Okay, what's up, guys? Welcome back. All right, part 2 of Duality. So, last time we wrapped up by talking a little bit about the annihilator of a subset. So recall, U0, the annihilator of U, is the set of all phi in V prime such that phi of U is equal to 0 for all U in big U. Okay, so these are just all of the linear functionals that vanish on that subset. That is, are equal to 0 for every element in that subset. Now, in the case where U is a subspace of V, and V is finite dimensional, we get a very nice formula. This is our next result. The dimension of the annihilator is just the dimension of V minus the dimension of U. This is kind of cool. All right, so let's go through and prove this one. All right, proof. Here's the gist. So, define I in LUV by, and this is going to seem weird, IU equals U. Okay. Why am I calling it I? I'm calling it I because it's just inclusion. So here's the idea. If U is a subspace of V, then everything in U is also in V. So I can map the stuff in U to stuff in V by just sending it to itself. It's pretty much the easiest possible map. It's not quite the identity, but it's essentially the identity up to just putting the codomain into a bigger set. It's an inclusion. All right, so the dual of this map, I prime in V prime, or I should say this, I prime in the linear maps from V prime to U prime. Okay, remember, if you have T in LVW, we can take its dual map, T prime, in L, W prime, V prime as follows. Here's the idea. You've got V, you've got W. T takes you over here. If you had some sort of a way of sending something from W, say some phi, to the underlying field, that is something in W prime, then using T, you get a new way to send V to the field. That is, you send stuff through T first, and then you map it through phi. So this is T prime of phi. That is, we take linear functionals on W, things that send W to the field, and we send them to linear functionals on V, things that send V to the field, and we do it just by following the arrows. So we've got a linear map from U to V. We can take its dual. This is a linear map from the space of linear functionals on V to the space of linear functionals on U. Now, all we have to do is use the fundamental theorem of linear maps. By the fundamental theorem of linear maps, the dimension of the range of I prime plus the dimension of the null space of I prime is equal to the dimension of V prime. Okay. But notice, what is the null space of I prime? Well, the null space of I prime, here, let's be careful here, let me make that like it look like a set bracket. Okay, the null space of any linear map is just all the stuff that gets sent to 0, right? So we're looking at phi in V prime such that I prime of phi is 0. Okay, but what is I prime of phi? Well, just looking at the definition of the dual of a linear map, we know that T prime here, as we drew it, well, all you do is you do T first, and then you do phi. Okay. So this is just phi in V prime, such that doing phi after doing the inclusion gives you 0. But the inclusion just takes things in U and sends them to the same U, but living in V. Oh, wait a second. This just says that this is the set of phis in V prime such that phi of U equals 0 for all U in U. Oh, so the null space of the inclusion maps dual is the annihilator of U. Whoa. That's pretty nice. Okay, we can put this up in here, and now we've got one of the things we want. We've got the dimension of U naught, the annihilator of U. Now we have to get a dimension of U and a dimension of V. Since we have shown that the dimension of V is equal to the dimension of V prime when V is finite dimensional, we have that the dimension of the range of I prime plus the dimension of the null space of I prime, which we know is just the dimension of the annihilator of U, is equal to the dimension of V. Okay. Hence, if dim range I prime equals dim U, we are done. That is, if this thing, just subtract it over to the other side, you would get dimension of U naught is equal to the dimension of V minus this thing, the dimension of the range of I prime. If that's equal to U, then we're all finished. All right, so let's think about this range here. Now, okay, here's the gist. So, what can we do? Notice the range of I prime is equal to, well, where does I prime live? It's linear functional, sends linear functionals in V prime to linear functionals in U prime, or linear functionals on U. So this is psi in U prime such that there exists some phi in V prime where I prime of phi is psi. So it's all of the linear functionals you can get by punching them through I prime. Okay, but this just says we have psi in U prime such that, well, there exists some phi in V prime with phi of U equal to psi of U for all U in U. Since I prime of phi is just phi composed with I, meaning that it's just phi restricted to U. Oh, okay, that just means that they agree on elements of U. Oh, okay. Now, here's the idea. Okay. Since every psi in U prime can be extended to a linear functional on V, we proved this in the homework. That is, we showed that if you had a linear map defined on a subspace, then you could extend it to a linear map defined on the whole space. All right. This says that the range of I prime the dual of I is precisely equal to u prime, i.e., I prime is surjective. Oh, okay. But notice the dimension of u prime is equal to the dimension of u. So we are finished. That is, we showed that the range of I prime is u prime, and the dimension of the range of I prime, here we go, is equal to the dimension of u. Nice. All right, so we've got a good formula for the dimension of the annihilator of a subspace of a finite dimensional vector space. Pretty cool. Easy enough. Maybe not that easy. That was actually kind of a fun, maybe slightly tricky proof in a certain sense. Actually, I think using the inclusion there is maybe not totally an obvious thing to do, though once you see it, it's not a terrible trick. But some of these things here are, proofs by contemplation. You have to just kind of stare at it for a little bit and think about it and go, oh, wait, oh, yeah, okay, that makes sense. Yeah. All right. So the next one, let's suppose that V is finite dimensional. All right, what we want to do is understand when a subspace U of V has an annihilator that is trivial in some sense. That is either just the zero subspace or the entirety of the dual space. So what subspaces get mapped to stuff with not that much information? Well, the answer to it, as we'll show, is that the only time that the annihilator of a subspace is just the zero map is when that subspace is the whole space. And the only time that the annihilator of some subspace is all of the possible linear functionals is when that subspace is just the trivial subspace consisting only of the additive identity in the vector space. Let's do the proof. I think it will become a little bit clearer once you see where this comes from. So, for part A, here's what we get. I'm just going to write it like this. U naught is trivial. Okay, let's start with that. Well, I claim that this is certainly only the case if the dimension of U naught is equal to 0. After all, there's only one zero-dimensional subspace. It is the subspace consisting only of 0. Okay, well, what is the dimension of U naught? It is the dimension of V minus the dimension of U. Okay, and from here, we can go a little bit further, and this says that the dimension of V is equal to the dimension of U. But wait, there's only one subspace of V that has the same dimension as V. That is V itself. Huh! Crazy! We did it! Okay, part A, not too bad. What about part B? Well, it is a similar line of reasoning. It's not too terrible. U naught equals V prime, the annihilator of U, being equal to V prime. Well, it certainly means that they have the same dimension. The dimension of U naught is equal to the dimension of V prime. Well, let's just use the formula we just did before. We know how to write the dimension of U naught, the annihilator of U. It's the dimension of V minus the dimension of U. But wait, I know the dimension of V prime is the dimension of V. Oh, okay. A vector space and its dual have the same dimension, provided they're finite dimensional. Okay, now from here, let's just subtract the dim V from both sides. I'll get a minus dim U equals 0, but why not just turn that into a positive dim U equals 0 by multiplying both sides by -1? Oh, there's only one zero-dimensional subspace. It's the trivial subspace with only the 0 vector. Huh, that is a pretty clever little trick, eh? We can fully characterized when the annihilator is boring. That is, if it's the trivially small or the trivially large subspace of a given vector space. Oh, or of the dual of a given vector space. All right, let's keep it going. Okay, hopefully this isn't getting too overwhelming. I know there's a lot of different things flying around, but just take a breather if this is starting to feel complicated. Look back at your notes, refresh your memory on what all these things are. It's mostly just new notation. We're actually talking about a simpler case of map than what we've talked about so far. In the last few sections, we've been talking a lot about linear maps from V to W. Here we're just talking about linear maps from V to a fixed W, where W is the field. So in many ways, the difficulty in this section is just notation. If you look back at the notation, you will probably be able to unconfuse yourself if you are feeling confused right now. So if you're feeling confused, do that real quick. But if not, let's keep going. Okay, so we just figured out what the dimension of the annihilator was, and we used it to characterize the cases when it was boring. That is, when it was the entire dual space or only the zero map. So what about duals of linear maps? Well, we'll prove here, first off, that the null space of the dual of a linear map, T, is the range of T's annihilator. And then as a pretty immediate consequence from that, using the fundamental theorem of linear maps, we will get that the dimension of the null space of T's dual is the dimension of the null space of T plus the dimension of W, its codomain, minus the dimension of V, its domain. Okay, cool, let's start. So B, I promise, is actually a very easy part. A is the only part that we actually have to do all that much for. So let's suppose that phi is in the null space of T prime. So 0 is equal to T prime of phi. That's what it means to be in the null space. All right, and keep track of it. So the dual of a linear map, if T is a linear map from V to W, then its dual will be a linear map from the dual of W to the dual of V. So this means that this is the 0 functional on V, just to be clear. But you don't need to think too much about that. It's just a 0, right? So you can just think of it like that. Just remember how T prime is defined now. It is phi composed with T. Okay, there we go. Thus, for every V in big V, since this is the 0 functional on V, phi of T of V is equal to 0. Oh. Hence, phi, well, phi vanishes on TV for every V. Wait, that means that it's in the annihilator of the range of T. It kills all the stuff that's in the range of T. That is all of the TVs for any V and V. Ah, okay. Very cool. So, the null space of T prime is contained in the range of T's annihilator. Now, suppose that we have, say, some psi in the range of T's annihilator. Okay. Then, psi of T of V is equal to 0 for every V in V. Oh, okay. We're just basically going to undo this calculation, i.e., T prime of psi of V, so whatever that functional is, evaluated at V is 0 for all V in V. Oh, okay. So, notice This means that psi is in the null space of T prime. After all, it sends it to the 0 map. That is the map that sends every v and v to 0. Oh, okay. T prime of psi is the 0 functional. So psi is in the null space of T prime. Hence, null T prime contains the range of T's annihilator. So we've shown that they're equal. Null space of T prime, the dual of T, is equal to the range of T's annihilator. All right, so we've got the first one down. What about this second one? Well, for the second part, observe. Here's what we'll do. What do we want to show? We want to show the null space of T has dimension dim null T plus dim W minus dim V. All right, so dim null T prime. Well, this is the dimension of the range of T's annihilator. But what did we show just a minute ago? Well, we showed that the dimension of the annihilator of something is the dimension of the whole space minus the dimension of that something. Okay, so the dimension of the range of T's annihilator will be equal to the dimension of W minus dim range T. Very cool. Okay, and now once I'm here, I'm pretty much done. After all, I know the formula for the dimension of the range. So here's what we'll do. This is just from the fact that since dim V is equal to dim null T plus dim range T, we can rewrite dim range T, the dimension of the range of T, as the dimension of V minus the dimension of the null space of T. Okay, now I'm going to rewrite that right here. Okay, and if you believe it now, wait a second, we've pretty much got it. I just have to rewrite dim null T, since I'm pulling that minus on through, plus dim W minus dim V. Dim null T plus dim W minus dim V. We did it. We're done. All right, not terrible. That was just a straightforward use of the fundamental theorem of linear maps, along with the first thing we proved today. Easy. So let's do something else. Let's use this. This is a fast one, another easy one, mostly just definition chasing. So we're going to say, hey, let's let V and W be finite dimensional. Let's let T be a linear map from V to W. Then, dualizing changes surjectivity to injectivity. Huh, kind of interesting. Let's prove this. This is kind of the whole business I said about dualizing, letting you essentially flop the domain and codomain around. That's kind of the gist of it. So here's how it works. If T is in L, VW, and is surjective, then the range of T is equal to W. That's what surjectivity means, right? Okay. But here we go. Range T equals W if and only if the range of T's annihilator, or the annihilator of the range of T, is trivial. Ooh, where did we get that? From this last one. The annihilator of something is trivial precisely when that something is the whole thing. But that's what we're saying. That range t is the whole thing. So its annihilator is trivial. Oh, okay. Cool. All right. But wait, the range of t's annihilator, we know what that is. That's the null space of t's dual. Oh, okay, so go on up and see null space of t prime is the annihilator of its range. So this is the null space of t prime. We know that that's trivial. But if the null space of t prime is trivial, then t prime is injective. So we are done. Nice. We used kind of a few of them right there. Nice. All right. All we had to do is we had to say, hey, look, the range is the whole space. Well, that means that the only thing that's going to vanish on all of the range is the linear functional that vanishes on every part of the whole space. It is precisely the zero map. So the annihilator is just the zero map. But we now know what the annihilator of the range is. It is the null space of the dual. It's the first thing we proved on this page here. And this means that the null space of t's dual is trivial, which is a fancy way of saying that t's dual is injective. Not so bad. All right. Let's see if we can characterize something about the range of t prime now. So we showed that the null space of t prime is the annihilator of the range. Maybe we can show that the range of t prime has something to do with the null space of t. That would be kind of nice. Let's find out. Okay, so let's see what's going on. So we've got v and w finite dimensional again, t, a linear map from v to w again. Here's what we're going to claim. We're going to claim that the range of t's dual is the annihilator of the null space of t. Do you see the nice symmetry? The annihilator of the range of t is the null space of t prime, while the annihilator of the null space of t is the range of t prime. You just flip null and range, and you turn primes into zeros. What a nice formalism. Consequently, since we know that we know a nice formula for the annihilator of something, we will get that the dimension of the range of t prime is equal to the dimension of the range of t. Kind of nice. So let's prove it. All right, for part A. For part A, we have the following. Well, the dimension of the range of t prime, well, we know what the dimension of the range of t prime is. It's the dimension of w prime minus the dimension of the null space of t prime. This is just the fundamental theorem of linear maps applied to t prime. All right, so from this, I know that the dimension of w prime is just the dimension of w. After all, the dual space and the original space have the same dimension. And I know what the null space of t prime is. It's the annihilator of the range of t. We just proved that. Okay. So you've got dim w minus the dimension of the range of t's annihilator. But wait a second. Okay, sorry, slight technical difficulty. Okay, so you've got the dimension of w minus the dimension of the range of t's annihilator. Now, do you remember any formulas involving the dimension of an annihilator? Maybe this first little bit we proved today, where we said the dimension of an annihilator is the dimension of the whole space minus the dimension of that subspace. So this says dim w minus, well, what is the range of t's annihilator a subspace of? Or what is the range of t a subspace of? It's a subspace of w. Dim w minus dim range t. But hey, wouldn't you know it? This just gives me the dimension of the range of t. since you've got dim w minus dim w, and you turn this minus over here into a plus when you carry it on through. Oh, would you look at that? We've got the dimension of the range of t prime equal to the dimension of the range of t. Oh, that's a terrible A in my writing of range. Okay, let's do part B. For part B, notice now, we want to show that the range of t prime is the null space of t's annihilator. Now, to do this, we're going to have to think for a second. So, let's start out by doing something other than this kind of chain of equalities thing that we've been doing a lot of lately. Yeah? Okay, so we're going to go back up, and we're going to try to do this in a little bit more engaged with the process manner. So let's take some phi in the range of t prime. Okay. Oh, suppose phi is in the range of t prime. Then there exists some psi in w prime such that t prime of psi is equal to phi, right? Okay, and I'll even put a parenthesis around that if you want to see it like that. For some reason, we've been writing parentheses, even though we normally write linear maps without them. Maybe just because it makes it slightly easier to see what's going on. Okay, now, if v is in the null space of t, then phi of v is equal to, well, that's t prime of psi evaluated at v, which is just equal to psi of t of v. But wait, t of v, if v is in the null space of t, is just 0. So this is psi of 0, and psi is linear. That's 0. Oh, okay. Hence, phi is in the null space of t's annihilator. That is, there's a linear functional that vanishes on the null space of t. Oh, so the range of t's dual is contained in the annihilator of t's null space. Now, let's go the other way. Or, even easier, we can go the other way. We can try to show that the null space of t's annihilator is contained in the range of t's dual, and thus show that they are equal. Or maybe a little bit easier, we could use this first part, and we could just say, hey, check it out. The range of t prime, if we can show that it has the same dimension as the null space of t's annihilator, then this containment says that they're the same thing, right? That is, if you have a subspace that has the same dimension, it is the whole space, right? So let's do that. To show that the range of t prime is equal to the annihilator of the null space of t, we show they have the same dimension. Okay, so how can we do this? Notice the dimension of the range of t prime. Well, we know what that is. It's the dimension of the range of t. Just prove that right up here. Yeah? First part of this this proof now. All right. But I know what the dimension of the range of t is. It's the dimension of v minus the dimension of the null space of t. Hey, wait a second. Dimension of v minus the dimension of something, that's equal to the dimension of that something's annihilator, right? So, dim v minus dim null t, this is dim null t's annihilator. That's the dimension of the annihilator of null t. Oh, so range t prime equals null t's annihilator. After all, one is contained in the other, so it's a subspace of it, and it has the same dimension as the thing it's contained in, it is that same exact space. Nice. All right. We get a really clean little consequence from this. So if V and W are finite dimensional, then T is injective if and only if T prime is surjective. This has such a nice pairing with this T surjective, implies that T prime is injective. This says that when you dualize, you flip injectivity and surjectivity. Oh, that is nice. That is super cool. It tells you that dualizing makes your life easy. Every time you wish that you had surjectivity, but you don't, you've only got injectivity, dualize. Now you got surjectivity. Every time you wish you had injectivity, but you don't, you only have surjectivity, dualize. Now you got it. It's a good tool. We're going to use it a lot. So let's prove it real quick. All right, proof. Quick proof. Okay. T is injective if and only if its null space is trivial. All right, that only happens, we know, if the annihilator of the null space is every single linear functional. Oh, wait a second. But the annihilator of the null space of T, that's the range of T prime. And that only happens when T prime is surjective. Nice. That was easy. All right, let's tie it on back to what we talked about last week with matrices. In fact, you'll see that dualizing things is an operation you are already familiar with, but just presented in an abstract form. It maybe has felt like this is weird and new and hard and complicated, advanced. It is not. I will show you that all we did is turn everything on its side. The dual of a linear map, I claim, is just the transpose of the matrix of that map. That is, we just literally flipped the matrix across its diagonal. We just turned it sideways. If you're thinking about just, looking at like a vector, basically, we're saying, hey, turn your vectors sideways. Now they're linear maps from the vector space to the field. Oh, whoa. All right, let's write it out. Here's the idea. So, all we have to do is a little bit of straightforward engagement with the definition of the matrix of a linear map. So, notice, all right, if, maybe I'll write it this way. I'll say this. I'll try to do this in like a pithy way. So if psi 1 through something is a basis, so psi j is a basis for, I should make sure that I'm making good sense of this. It should be W prime, yeah. And phi 1 through phi n, I shouldn't say j. Let me make this through m. How about m? And m and n, that'll be easier, is a basis for W, where psi 1 through psi m, and this is maybe where the part of it that gets confusing is. So we're taking matrices of linear maps. These have to be done with respect to bases. Maybe I should have started by saying this, but I guess it was kind of just in the background and hiding. Here's the idea. We should take this to be the dual basis of something. Said another way, and maybe I haven't shown this, but if you want to see it, if you can, it is not a terribly hard fact to show. Every basis of the dual space is the dual basis of some basis of the original space. Where this one is the dual basis of W1 through Wm, and phi 1 through phi n is the dual basis of V1 through Vn. Then we have the following. Here's the idea. T prime of psi j, of the jth basis vector in this dual basis. Okay, well this is equal to the sum from, I'll take it from like r equals 1 up to n of, now I should be careful how I write this, it's the matrix of t prime, and this will be the r jth entry? Yeah, the r jth entry, and next to it will be phi r. Too many different indices flying around. This is all these parts can be kind of annoying. But basically, hey, just think about it. It says that when you map on through the jth basis vector, you can write this as some linear combination of the other basis vectors. The coefficients of it are just the things in the jth column of the matrix. All right, cool. Now, apply this to VK. Okay, so let's do it. So we've got T prime of psi j applied to VK. Well, this is equal to the sum from r equals 1 to n of the matrix of T prime, Rj, phi r applied to Vk. Okay. But wait a second. What is this one over here? Well, this is just psi j of T of Vk. Okay. Cool. And what is phi r of Vk? Well, if this is the dual basis of that guy, then it's going to be 0 unless r equals k, right? So on this side, well, I won't even write that vertically, I'll just write it this way. I will just write it as the matrix of T prime. This is the kjth entry. Kj. Oh, wait a second. Think about this. So, we also know that psi j of T of Vk is equal to psi j, well, it's of tvk, but we should write what tvk is. It is the sum from j, or maybe I'll even write it the same way, from r equals 1 to m of the matrix of T, where I take r comma k, and this is WR now. Oh, okay, yeah, so I can send a basis vector vk through T and write it as a linear combination of the w's. The coefficients come from the matrix of T with respect to those two bases. But by linearity, I can split this up. So this is the matrix, a sum from 1 to m of the matrix of T, Rk, phi j of WR, but wait a second. Psi j, not phi j, sorry, I'm writing my psi's and my phi's too quickly. Psi j of WR. But wait a second. Psi? This is the dual basis of the w's. So the only one that isn't 0 is when j is equal to r, right? Oh, and then we'll get 1, and this gives us the matrix of T, J, K. So, the matrix of T prime, Kj, is equal to the matrix of T, J, K. The kjth entry of one is equal to the jkth entry of the other. Oh, transpose. So, the matrix of T prime is equal to the matrix of T transpose. Right? All we got, or maybe it reads awkwardly when I say the so's twice. maybe I should just say and. All we had to do was get that they're the same except for the indices being switched. Then just transpose it, and now you got it. Super cool. Easy enough. But hey, wait a second. This gives us an alternate proof of the fact that the column rank of A equals the row rank of A. Since the dimension of the range of T prime and the dimension of the range of T are the same. Huh. Kind of cool. Kind of nifty, right? Oh. Tablet's bugging out. There we go. Kind of neat. We'll end it there for today. What a fun topic. Next time, we'll get into using duality to do a lot of new neat stuff. I'll see you then.